Hi, it's Dr. T, and I'm back with that question that we talked about today. That is how to predict energy changes in reactions using that method of bond energies. Um, so we talked about how the first example we use is to look at this table, and this table shows us the reactants at this level, hydrogen molecules plus oxygen molecules. They go to form two molecules of water. We can see that down here. And the mechanism, the idea of how do we do this computing and find out the energy changes minus 498 kilojoules. What we do is we actually use the method of bond energies. It turns out that chemists have measured and tabulated lots of different bond energies, and the values that are in this table will tell you roughly what a bond energy is for a different type of bond in lots of different and nearly all molecules. And if we want to know where the hydrogen oxygen bond energies, we look over on the oxygen here and we go down the hydrogen table here, and we got hydrogen here. It's 467 kilojoules per mole. So the strategy is that we're going to take our reactants and we're going to blow them apart into atoms. We'll compute the amount of energy it takes to convert them into atoms. And then we'll talk about how much energy we get out when we can bring those atoms back to the configuration of the product. So you're going to need some Lewis dot structures to do this correctly. So if we look at water, we can find out a hydrogen molecule has a hydrogen-hydrogen single bond. We have to break two of those to make two hydrogen atoms. So each hydrogen-hydrogen bond is worth 436 kilojoules per mole. Multiply that times 2, we get 872 kilojoules. We still have to break the oxygen molecule into two, and that's going to cost us an extra 498 kilojoules. So we've got to put in a combination of 872 plus 498 kilojoules to make 4 hydrogen atoms and 2 oxygen atoms in the gas phase. Now we want to combine those together and make water. And each water molecule has 2 oxygen-hydrogen bonds, so we're making a total of 4 oxygen-hydrogen bonds. So let's go. Here's hydrogen. Here's oxygen. 467 kilojoules per mole. We're making 4 of those, so we have 4 times 467, which is minus 1868 kilojoules. So that's how much energy we get back. So the total energy is going to be the energy we put in, which is going to be positive, because that's going uphill. We have to rip atoms apart, so we have to put in energy. That's 498 plus 872 minus the energy we get back from forming the bonds, which is 1868, gives us a net change of minus 498 kilojoules. All right. So that's illustrated a simpler example. Or let's take a look at some different molecules. Let's look at combusting methane to give water and carbon dioxide, not oxygen. This should be CO2. My bad here. So it's going to be methane plus oxygen give us CO2 plus water. That's the blue. We have to balance the equations, so we put the 2 coefficients in green, and that gives us 2 oxygens and 2 CO and 2 waters. So now we're balanced. Now we take methane. We have to draw the Lewis structure for that. So we draw the 4 carbon hydrogen bonds. We draw the Lewis structure for oxygen. We have an oxygen-oxygen double bond. CO2 has this Lewis structure. And finally, water has this structure we saw above, which has 2 oxygen-hydrogen bonds. Then we go back and say we're going to have to break 4 carbon-hydrogen bonds and 2 oxygen-oxygen double bonds. But we're going to get back 2 carbon-oxygen double bonds and 4 oxygen-hydrogen single bonds. And so now we have to go into the table and find the bond energies here. So carbon-hydrogen is, go down, here's a hydrogen, 416, so 4 times 416. Oxygen-oxygen double bond is 498. So these cost us energy. They stay in red, like a good accountant would say. The energy we get back is going to be 2 carbon-oxygen double bonds. Here we go, 803. So 2 times the 803 minus 4 times the oxygen-hydrogen bond energy, which is 467. And we add that all up, we get 814 kilojoules per mole of methane. So that's how much energy you get per mole of methane. And this agrees pretty well with the number we saw on the previous page. Finally, we can compute the energy density. And I've got to hide our stupid menu bar. So the energy density is equal to the minus the energy per mole divided by the grams per mole. So the energy per mole is the number we computed up here. The grams per mole is going to, of the fuel, which is methane, is the molar mass of the fuel. So we take 814 kilojoules per mole of methane, divide that by 16 grams per mole for methane, and we end up with 51 kilojoules per gram of methane as the energy density. So I hope you found this useful. See you in class next Monday.